On the 7th of October 2025, the European Space Agency unveiled the inaugural official photographic captures of Comet I Atlas, an interstellar wanderer gliding near Mars. The global populace anticipated breathtaking details. Instead, a storm of discontent erupted, presenting merely a fuzzy point of light, a disconcerting quietude from NASA, China, and the UAE, and a complete absence of the crisp data that everyone had eagerly awaited. Why did the most anticipated celestial passage in years, the Martian flyby that captivated the internet, yield naught but a cascade of questions? And what exactly are these agencies endeavoring to conceal behind their pronouncements of technical difficulties? When amateur astronomers, with their backyard instruments, manage to produce clearer images than missions costing billions, and whispers of improbable chemical compositions begin to circulate, only one truth emerges. The genuine narrative is only just commencing. So, what vital information are we being deliberately kept unaware of? At 9:22 UTC on the 7th of October, the very first official imagery from the ESA pertaining to Comet IAT became accessible across agency platforms. Within mere minutes, prominent science communicators worldwide, fervent space enthusiasts, and even purveyors of internet humor disseminated the identical, profoundly underwhelming frame. It depicted a faint, indistinct spot, scarcely more luminous than the surrounding digital interference. By midday, ESA's Comet imagery was trending across 4 different languages. Hashtags such as FusiDot and Where Are the Pics flooded platforms like X and Reddit, where armchair investigators meticulously scrutinized every single pixel. The wave of indignation extended far beyond mere disappointment. Juxtaposed comparisons flooded the digital sphere, showcasing captures from amateur telescopes that possessed demonstrably more discernible detail than those obtained by the billion-euro Mars orbiter. Accusations of clandestine actions were leveled at the ESA, amplified by the synchronized reticence from NASA, China, and the UAE. With each unanswered query, the clamor for a forthright explanation intensified. The KSSIS camera, an integral component of the ExoMars Trace Gas Orbiter, was never conceived with the objective of tracking interstellar visitors. Its primary function is to meticulously map the Martian surface in vibrant color, documenting landslides and scrutinizing subtle shifts in dust and frost. When reoriented to capture I-Atlas, situated 30 million kilometers distant, its design limitations became acutely apparent. At such an expanse, each pixel captured by CASS encompasses approximately 340 kilometers. This is an area vast enough to completely encompass entire Martian volcanoes, let alone a cometary nucleus that might measure a mere few dozen kilometers across. The camera's inherent resolution, a mere 11.36 microradians per pixel, imposes an insurmountable barrier. Regardless of the perfection of its focus or the duration of its exposure, any entity smaller than a single pixel inevitably devolves into an indistinct blur. It is essentially light diffused across the sensor. Nick Thomas, the lead investigator, characterized the endeavor as a formidable challenge, even to achieve basic detection. The comet was at least 10,000 times fainter than the terrestrial features that Casser Eyes was engineered to photograph. The team undertook the arduous process of stacking multiple exposures, meticulously refining the tracking, and extracting every conceivable bit of signal from the inherent noise. The resultant fuzzy dot was not an artifact of concealment, but rather a testament to the ultimate technical limitations. The coma, an expansive envelope of gas and dust stretching for thousands of kilometers, dissolved into the backdrop, while the nucleus itself remained entirely obscured. The immutable laws of physics prevailed. At these immense distances, even the most sophisticated instrumentation stationed on Mars can merely corroborate the comet's presence, failing to unveil its intrinsic secrets. The public yearned for a detailed portrait. The camera, however, could only provide a mere fingerprint. The subsequent prospect of acquiring granular detail would necessitate the deployment of a different instrument or an entirely altered orbital configuration. HiRISE, the high-resolution camera aboard NASA's Mars Reconnaissance Orbiter, was anticipated to be Mars's decisive advantage. Its advanced optics possessed the capability to discern rover tracks from orbit, and at a distance of 30 million kilometers, it held the promise of offering at least a fleeting glimpse, perhaps even a few pixels, of Atlas's core. However, as the celestial rendezvous transpired, HiRISE abruptly ceased communication. The United States government shutdown, which commenced on the 1st of October, effectively paralyzed the entire operational chain. This meant no command uplinks, no status reports, and critically, no dissemination of public data. The official communication channels remained eerily silent for an extended period. Amateur and professional astronomers alike repeatedly refreshed the HiRISE archive, desperately seeking any indication of the planned observations. Nothing materialized. Even the preliminary planning documentation, typically published in advance, was conspicuously absent. With NASA's data streams effectively frozen, speculation naturally gravitated towards Mars's other orbiting observatories. China's Tianwen-1 orbiter and the UAE's HOPE mission had both been diligently tracking the comet's approach. Yet neither entity released any images, official statements, or even a straightforward denial. The silence only deepened, becoming more profound. While some readily attributed this lack of information to the government shutdown as the most plausible explanation, others harbored doubts, questioning why three separate space agencies, spanning two continents, would all concurrently fall silent. In the vacuum left by the absence of concrete data, conjecture and rumors proliferated. Each passing hour without a substantive answer only amplified the focus on what was conspicuously missing. It wasn't just a demand for sharper imagery. It was the pervasive sentiment that the world's most sophisticated observational instruments were being deliberately muted. The absence of HiRISE's contribution became the overarching narrative. The conspicuous omission of this prized observational asset left the Internet ravenous for external validation, and every unanswered question served to fuel the growing suspicion that something was being intentionally kept from public view. In the hours immediately following the widespread dissemination of the European Space Agency's indistinct depiction of the comet, a fervent battle of imagery commenced. Amateur astronomers, from the farthest reaches of Italy to the shores of Japan, began sharing their own renditions. Some featured extensive stacks of dozens of captured frames, while others employed AI upscaling filters, promising to reveal hidden structural details. By the 9th of October, the Internet had bifurcated into two distinct factions. One group vociferously asserted the presence of a distinct core, and possibly even indications of a tail or active jets, arguing that amateur telescopes had unequivocally surpassed the capabilities of a billion-euro orbiter. Conversely, the other group issued cautionary pronouncements, asserting that any perceived novel detail was merely an illusion, a phantom conjured through excessive processing and wishful thinking. Maya Trin, a highly regarded comet enthusiast hailing from Melbourne, emerged as the de facto spokesperson for the initial faction. She published a series of images, each subjected to progressively more intensive processing, complete with annotations highlighting what she identified as non-random linear features emanating from the nucleus. Her online posts garnered tens of thousands of shares, igniting a surge of speculation about what professional astronomers might be overlooking or deliberately concealing. However, professional astronomers countered these claims by presenting side-by-side comparisons and conducting rigorous simulations. Their analyses demonstrated how the superposition of faint frames could inadvertently amplify background noise, transforming cosmic rays and aberrant pixels into spurious structural artifacts. They argued that AI upscaling, by its very nature, only served to sharpen these imperfections, rather than enhance the scientific validity of the observations. The discourse rapidly devolved into intricate technicalities. Terms such as sigma clipping, deconvolution, and pareidolia became ubiquitous on online forums as users attempted to reverse engineer the truth from the raw data. Some observers astutely pointed out that even a perfectly composed stack, given Cassius's resolution of 340 kilometers per pixel, could never resolve a cometary nucleus that was a mere fraction of that size. Closer examination revealed that the sharpest amateur images often relied on aggressive enhancement techniques that introduced more ambiguities than definitive answers. With the continuous emergence of each newly processed frame, the demarcation between genuine discovery and manufactured illusion became increasingly blurred. The Internet's insatiable appetite for intricate detail outstripped the capacity of the available data to provide honest answers, and the imperative for meticulous, transparent analysis grew ever more insistent. If any substantial revelation was indeed present, it would necessitate more than mere software manipulation to substantiate. Anonymous postings began to circulate even before the initial ESA frames had concluded their trending phase. As the informal network of rumors expanded, so too did the demands for tangible, verifiable data. The Internet's voracious hunger for answers now hinged upon the subsequent dissemination of measurable facts. Precise trajectory calculations, radio signal analyses, or any information amenable to empirical testing. Until such time, the onus of proof remained firmly with those making claims, not with their skeptics. Mallory Lefferland, the shift lead for the Perseverance rover, encountered a predicament that deviated significantly from the mission's established protocols. The rover's navigation camera was never designed for the pursuit of comets, let alone one hurtling past Mars at a velocity approaching 90 kilometers per second. Nevertheless, on the 7th of October, she authorized a specialized sequence comprising 10 minutes of uninterrupted skyward exposures, with the hope of detecting a faint trace of I-Atlas as it traversed Jezero's field of view. The raw photographic data revealed a singular faint streak. It measured slightly more than a single pixel in width, extending diagonally across the entire image. At first glance, it bore the appearance of a digital anomaly or an impinging cosmic ray. However, the precise timing of its appearance corresponded with the comet's predicted passage with remarkable accuracy, to within mere seconds. The mathematical underpinnings of this observed streak were straightforward, but its potential implications were anything but. At a velocity of 90 kilometers per second, I-Atlas would traverse approximately 54,000 kilometers within a 10-minute interval, a distance closely mirroring the length of the observed NavCam streak. If the camera's exposure had remained active for the entirety of the sequence, this streak would precisely align with the established model for motion blur. This phenomenon occurs when a distant object, moving at a considerable speed and too faint to be resolved in a single exposure, becomes discernible as an elongated smear when integrated over a period of time. However, a critical caveat existed. If the camera had captured only a brief, isolated exposure, the source of the streak would necessitate being substantially closer, perhaps even orbiting Mars itself, to produce an identical linear distortion. In the absence of access to the original FITS headers, the precise exposure duration and the cadence of image acquisition remained irrevocably fixed within the rover's operational logs. Consequently, every subsequent calculation was critically dependent upon this missing piece of information. Was this observed phenomenon the comet itself, or rather a nearer celestial body that had flashed through the sky? Lefferland's decision transformed a nebulous rumor into a concrete, testable hypothesis. The NavCam streak thus emerged as the inaugural quantifiable datum within a landscape awash with speculation, presenting itself as a 54,000-kilometer question mark. For the subsequent phase of radio signal analysis and trajectory verification, The derived mathematical parameters would establish the definitive threshold for what constituted valid evidence and what remained merely extraneous noise. A vector originating from Jezero crater on the 7th of October pointed almost directly towards a specific celestial region renowned for a singular enigmatic event, the WOW signal. In 1977, a radio telescope situated at Ohio State University detected a brief 72-second transmission at a frequency of 1,420 megahertz, corresponding to the hydrogen line. The origin of this signal was never definitively identified, but the precise coordinates have remained etched in scientific lore. Now, with I-Atlas passing within a mere handful of degrees of that particular patch of sky, the confluence of these events was simply too coincidental to dismiss. Online forums became abuzz with rudimentary calculations to replicate the intensity of the WOW signal emanating from a transmitter located 600 astronomical units away. A power output of at least half a gigawatt would be required, potentially increasing to 2 gigawatts if a highly directional dish antenna were precisely aimed at Earth. This represents the energy output of a major power station, focused as a concentrated beam through the vastness of space. Yet, despite the extensive online discourse, no public observatory released any hydrogen line data pertaining to the comet's passage. There was no coordinated listening campaign, no public dissemination of raw spectrum analyses, not even a confirmed negative result. The silence was no longer confined to the optical spectrum. It now extended to radio observations as well. The fundamental question lingered in the ether. Given the fortuitous alignment of celestial geometry and the availability of relevant mathematical models, why did no entity undertake the most straightforward investigative procedure? On the 29th of October, I-Atlas egressed behind the Sun from Earth's observational perspective, disappearing into a glare so intense that even the most powerful telescopes were rendered functionally blind. For a duration spanning nearly 40 hours, no ground-based observatory was capable of tracking its trajectory. The comet's solar elongation, its angular separation from the Sun, diminished to levels considered unsafe for all but the most robustly shielded instruments. During this period of observational blackout, every conceivable theory found fertile ground for proliferation. Certain astronomers voiced concerns regarding potential natural outbursts or the possibility of fragmentation, the common fate of comets subjected to intense solar forces. Others, meticulously scrutinizing orbital simulations, mused aloud about the potential for an orchestrated maneuver, something artificial unfolding beyond the visible horizon. The Galileo Project, a dedicated collective focused on the detection of non-natural technological signatures, announced a continuous round-the-clock vigil across all available radio and optical channels, in the fervent hope of identifying any anomalous phenomena as the object completed its perihelion passage. With the primary observational period obscured, the world was left to grapple with mere computational models and unverified conjecture. Upon I-Atlas's reappearance, its luminosity, orbital path, and any nascent fragments would serve as the next critical tests, evaluating both the inherent unpredictability of cosmic phenomena and the inherent limitations of our observational capabilities. The early days of November presented a series of crucial diagnostic tests for I-Atlas. Astronomers turned their attention to analyzing its photometric curves, diligently searching for abrupt decreases or surges in brightness that might indicate fragmentation. Orbital models, fed with newly acquired data, were run to detect even minute deviations in trajectory, serving as potential evidence of active jets, outgassing, or perhaps something far more inexplicable. Each measurement served as a pass or fail criterion. Did the comet's emitted light diminish as anticipated, or had it fractured into multiple pieces? Trajectory predictions were rigorously compared against observed reality, searching for any deviation that lacked a plausible scientific explanation. Concurrently, the JUICE spacecraft awaited its designated observation window later in the month. Its advanced instrumentation promised a novel perspective on the celestial body, but the processed data would not reach Earth until well into the year 2026. Until then, every subtle shift in the comet's trajectory or its observed brightness would function as a vital clue, and every instance of delayed data dissemination would continue to fuel global conjecture regarding what had ultimately survived its perilous solar passage. The celestial expanse of October was not solely occupied by the presence of I Atlas. Merely days prior to the comet's dramatic flyby of Mars, a near-Earth object, catalogued as 2025 TF, made an exceptionally close approach to Earth, slipping inside the orbital paths of GPS satellites with astonishing stealth. This asteroid, measuring merely a few meters across, eluded detection by all major survey programs until it was virtually directly overhead. This incident served as a stark reminder that even within an era of comprehensive sky monitoring, objects characterized by their small size and high velocity can still evade observation. Simultaneously, two distinct comets embarked upon their own unpredictable celestial journeys. Comet C 2025A6. Lemon began its brightening phase weeks ahead of its projected schedule, hinting at a potential outburst event. Comet C 2025R2SW garnered significant attention due to its remarkably close proximity to Earth, passing at a distance of a mere 0.26 astronomical units, thereby igniting hopes for the visualization of a prominent tail and simultaneously raising concerns about the possibility of sudden, catastrophic fragmentation. Each of these celestial occurrences underscored the inherent limitations of our current surveillance systems, illustrating that the next unforeseen event could originate from any direction and manifest at any scale. The overarching lesson is undeniable. The cosmos is replete with near misses, and our vigilant watch is perpetually incomplete. On the 7th and 8th of October 2025, the European Space Agency released the inaugural official imagery of Comet I Atlas. The initial depiction, consisting of a single blurred pixel, ignited a global discussion and calls for enhanced transparency. The limited detail observed was attributed to the inherent technical constraints of the gaseous instrument rather than any deliberate act of suppression. Nevertheless, the simultaneous silence emanating from High-Rise, Tianwen-1, and Hope created significant data voids that remain unexplained. Despite the widespread dissemination of viral amateur images and persistent rumors concerning unusual emissions or precisely executed maneuvers, no official corroborating evidence has been presented to substantiate these claims. The streak captured by the Perseverance navigation camera aligns with the expected motion blur for an object traveling at 90 kilometers per second, though alternative explanations cannot be definitively excluded. As I-Atlas transited behind the Sun during its perihelion passage, observers eagerly anticipated early November for any signs of fragmentation or trajectory alterations. The delayed JUICE observations, coupled with the recent close passage of near-Earth object 2025 TF, serve to highlight the ongoing challenges inherent in monitoring rapidly moving and unpredictable celestial visitors. To this day, the true nature of I-Atlas remains an unresolved enigma, underscoring both the limitations of our current observational capabilities and the paramount importance of open data dissemination within the field of planetary science.